Hey there, it's Miss B. In this video, we're looking at the Unit 5, Lesson 8, Cumulative Practice Problems for Illustrative Math, Algebra 1. So let's start with the first question here. We have an experiment. A scientist designs a can 20 centimeters in height. That sounds important, so I'm going to underline 20 centimeters. It can hold water, and a tube is installed at the bottom, allowing the water to drain out. At the beginning of the experiment, the can is full, and when the experiment starts, the water begins to drain, and the height of the water in the can decreases by a factor of 1/3 each minute. So decreasing by a factor of 1/3 sounds important also, so I'm going to underline that one. The first question they have for us is to explain why the height of the water in the can is a function of time. Well, this is what we're talking about when we talk about inputs and outputs. In a function, for each input, there can only be one output. So for us, our input, based on this sentence, we would always say output is a function of input. So height of the water is going to be the output here. Output. And then time would be the input. So for each input, there's only one output. That means for each specific time, there's only going to be one height of water that corresponds with it. Essentially saying the water cannot be two different heights at the same time. It would be physically impossible. So let's write that out in some mathematical terms. We can say at any point in time, or any moment in time, I'm saying point in time, there is only one height of water in the can. Okay, so now that we have thoroughly convinced everyone that this is a function, we're now going to write it in function notation. So we're going to use f of t, and t is going to represent minutes. So instead of saying that the height is equal to something and h is equal to, we're going to use f of t to represent this. But we're still going to use the basic pieces to build our equation. So that is going to be our initial value, which is the starting height of the water. And it said that at the beginning of the experiment, the can is full. So if the can is full, that means we are starting with 20 centimeters. Now, they did tell us it was decreasing, and they actually told us the factor. So we're not going to do 1 minus that factor. We are just going to use 1/3 here because they are already telling us that that is what the growth factor is. So it's decreasing by that factor of 1/3. And then t is going to be minutes, and so we would put t as our exponent on our equation here. So for part C, they're then going to have us go through and find some values at these different points in time. So I'm going to say I have t and f of t. Let's make a table of values. So starting with 0, and then they want us to do 1, 2, and 3. So we'll do 0, 1, 2, and 3. So at 0, and you can double check this by plugging in 0 for t, but at 0, our answer or our function value should always be our initial value or the number in front of our growth factor. So I'm going to use 20. And then as we go, we are multiplying that by our growth factor each time. So it turns out that 20, when I multiply it by 1/3, it has the same effect as dividing by 3, but it's also not going to give us whole numbers. So you can give a decimal approximation of this, but I am going to use improper fractions. I think that they're just the most accurate. So in this case, this would be 20 divided by 3, or 20 over 3. Now, if I divide by 3 again, I'm still going to have 20 in my numerator, but I'm now dividing by 9. And at 3, I'm still going to have 20 in my numerator, but I'll be dividing by 27. So if you want to check and you have decimal answers and you want to check them with mine, all you would have to do is plug those numbers, 20 divided by 27, into the calculator and see if it matches up with what you got by plugging in to maybe this function right here. Okay, so for the next portion, part D, they want us to now find at f of 4. So let's actually find f of 4. That's going to be the same as multiplying by 1/3 again. And if I took the 20 over 27 and followed that same pattern, I would still have 20 in my numerator, but now my denominator, multiplying by 3 again, I'm going to have 81. So this is the same as 20 over 81. You would also be able to plug in to a calculator 20 times 1/3 to the power of 4. But they're also asking us, what does this represent? So we are going to say, after 4 minutes, because 4 represents minutes. So after 4 minutes, the height of the water is. And then it is that 20 over 81. Or if you put this in decimals, it's going to be very close to 0.25. 20 over 80 would be 0.25, so 20 over 81 is going to be close. But we could say 20 over 81 centimeters, or we can say approximately 0.25 centimeters. One of those answers is exact with the improper fractions, and the other one is approximated, so that's why I like to use the improper fractions. Okay, so we have 2 more pieces here. After that, we want to sketch a graph, either by hand or using graphing technology. You can also probably plug these in and use graphing technology to help you with sketching your graph by hand. So let's make a graph. I'm gonna draw here with my black pen, kind of make myself some vertical and horizontal axes. And along my horizontal, I want to have time in minutes, so I'm just gonna say time. And, oh, actually I made that a little close to the bottom of my answer here, so I might move it up. That way I can actually put some numbers in there. I didn't think about that one. Okay, time, because I want to be able to put numbers underneath it. And then we want to put height along the horizontal axis here. Or I'm sorry, the vertical. Okay. Now for time, we have data for 0, 1, 2, 3, and 4. So I am going to have 0, 0. Or not 0, 0. I am going to have 0 on here. And so then I can just include 1, 2, 3, and 4. And you can really bring it out to 5 even if you wanted. But I'm going to try to just make mine evenly spaced. And since this is decreasing over time, I'm going to start at my initial value and kind of just make that the maximum of my graph. So I'll have 20 right here, and I'm going to estimate values for my different numbers because I have them all as improper fractions, but we'll sort of estimate some values here. So maybe I know halfway should be 10. So I can probably put like 15 and 5 here and just cut it into fourths as well. So I am now going to graph my points, and I'm going to use red in order to do that to help them stand out. So I know that I have 20 and 0. So at 0, the height is 20, and that's centimeters. At 1, we have 20 divided by 3. Now, 20 divided by 3 is going to be a little bit over 5. I want to say it's not quite 7. If I had 21 over 3, it would actually be 7. So we're going to put it just below where 7 would be. So it's going to be around here, above 5, but not quite 7. At 2, we have 20 over 9. And this is going to be around 20 divided by 9. Well, if we had 20 divided by 10, that would be 2. So this is going to be a little bit more than 2. So at number 2, I'm going to put it here. And that should be pretty accurate. And then for our time at 3, 20 over 27 is going to be less than 1. So it's going to be pretty close to our axis here. And if we wanted to even include f of 4, this is pretty close to 0.25. So we're going to have it almost even touching our axis, but the center of it won't be. So you can put some dots there, but the way that this is decreasing, you can also connect it because the water should be flowing out over time and it'll continue in that direction. So I'm going to put an arrow. Now, you could use graphing technology to help you with this, but I figured I would demonstrate doing some of the graphing by hand. But that is it for part E. We now have one part left. What happens to the level of water in the can as time continues to elapse, and how do you see this in the graph? So the water is decreasing as it goes, and we see our dots for our points getting closer and closer to 0. So that's how I'm going to explain it. I will say, I'll put this in blue again. The water is decreasing over time. Because, well, it's decreasing because it's emptying out of a tube in the bottom. So because it is draining out, we'll say I, because how do you see this in the graph is the question. So I said, I can see this. I can see the graph getting closer to 0. Closer and closer to 0. Okay. On to question 2. All right, so this is a different question, but we have a scientist who is measuring the height, h, of a tree each month, and m is the number of months since the scientist first started measuring the height of the tree. So this question is just asking us a couple things about whether or not this is a function. So is the height a function of the month? So basically, is the height a function of time? And explain how you know. So if we agree, then we're going to explain why we agree. And if we disagree, we're going to explain why we disagree. So in this case, is height a function of time? Just the same way as with our water, or the height of the water in the can, I would agree that this height is a function of time. So I'm going to say yes. The tree can only be one height at a time. Now they also want to know in the other direction. So they want to know, okay, if its height is a function of time, is the time in months potentially a function of height? And the answer to this is that it could be, but there's also a good chances that it's not. So it's very possible that this tree is the same height for 2 months in a row. So I am going to express that, I'm going to say if the height of the tree is the same for 2 months in a row, then it would not be a function. So if it's never the same height for 2 different months, then yeah, it would end up being a function. But I think it's probable that this tree could have been the same height 2 months in a row. So I'm going to leave that as my answer. So it's sort of conditional. But if I had to choose one, I would choose no, because it's possible that it's not a function. So that brings us on to the next page. Now, I know on the copy of this that I gave to my class, there was not a question 3, or question 3 sort of got cut off. So I am going to actually talk about question 3 and answer this here, but I realize that that may not line up with number 3 on your assignment. So it'll be a little bonus, I suppose. For number 3, we have a bacteria population that is 10,000 and it triples each day. So it is 10,000 and it's tripling each day. That is multiplying by 3. So we want to explain why it is a function. So why is the bacteria population a function of the number of days? This is the same thing as our previous one. There is only one output for each input. So for any specific day, there's only going to be one amount of bacteria. So there is only one amount of bacteria for each day. Because they're only going to measure the amount of bacteria like at that same time each day. And so they're not going to measure it and be like, whoa, there's 2 different amounts. They would only get 1 for each time that they measured it. So B asks us now, which variable is the independent variable in this situation? And in this case, that's going to be days or the time. But we're representing that with D. So we would say D is the independent. And you could say this is days since measured, or since first measured. And then they want us to write an equation. So relating B and D, the amount of bacteria. So I'm going to say the amount of bacteria, B, is going to be equal to my starting amount of bacteria, so 10,000, times my growth factor. If it's tripling, that's going to be 3, and that is going to be multiplied by 3 each day, so D as my exponent. And that's it for that question. Question 4 is another question about whether or not these things can be functions. So the position P of a minute hand on a clock. All right, well, let's draw ourselves a little clock here. I'll make a circle, and there we go. I was going to say the iPad will make it a little nicer for me. And I could draw my different, hands and everything on my clock. Maybe we'll do like the minute hand a little bit longer, and then I could have like my hour hand shorter, something like that. So they want to know, the first part of this that they're asking is the position of the minute hand a function of the time? So when I try to figure this out, I think, can it have two different outputs for every input? And in this case, the position is the output and the input is the time. So that minute hand cannot be in two different places at the same time. So there is only going to be one output for each input. So let's say that, yes, it is a function. So yes, oops, didn't mean to use my thick marker. Yes, for each time, right, or for each input. So for each time, the minute hand will only be in one position. It's not suddenly going to appear that there are 2 minute hands in 2 different positions for the same time. Now the second part says, is the time a function of the position? So what this is asking is, for any specific position of the minute hand, can there be more than one time? So to put things simply, this is not going to be a function. And the reason for that is every hour on the hour, my minute hand is going to be pointing straight up. Whether my hour hand here is pointing at like 2 or at 3 or at 4 or 6 or 8 or any other hour, the minute hand will always be pointing straight up. So if the position is the input and I say the minute hand is pointing straight up, that is not going to tell me one specific time. That's going to be potentially 24 different times. So we would say no, it is not. No, because the minute hand can be in the same position at multiple different times. And then I'm just going to kind of put in parentheses the example I gave, like noon, 1 p.m., 2 p.m., etc. My minute hand is going to be in the same spot, even though my hour hand is different. Okay, that finishes up question 4. Let's look at question 5. Question 5 says we have the area covered by a city, and that is 20 square miles. And this area is growing by a factor of 1.1 each year since it was a 20 square mile radius. So they want to explain why the area A covered by the city is a function of the number of years. And as most things with time, we are going to say because the city cannot cover 2 different areas at the same time. It cannot have two different like surface areas, I guess. It would only be one measurement at one time. So let's find a good way to say this. The city, we'll say the city can only have one area at a time. The city can only have one area at a time. Okay, and then for part B, they want us to write an equation for A in terms of T. So we can say A is equal to, and so that's the area. So we're going to start with the initial value, 20 square miles. That's how much it covered. And then they did tell us it has a growth factor of 1.1. So we will use those numbers. We're going to have 20. And then I like to put my growth factor in the parentheses and say 1.1. And then this is t in time, but t is years. So to the power of t and my exponent. And that's all for question 5. That brings us to question 6, the last question here. This graph shows an exponential relationship between x and y. We want to write an equation representing this relationship, and then answer part B and C afterwards. Those are going to deal with negative exponents and some things like that. So we need two things. We need an initial value and we need a growth factor. So the initial value, we're used to looking all the way over at the left, and that's not quite correct here because my axis for my vertical intercept is now in the middle. So we are going to use this point, which is labeled for us with numbers, which is nice, as our initial value. So 50 is when we have 0 as our input. So x and y, I am going to say that y is equal to 50. Now I need to figure out what my growth factor is, and then I will have x as my exponent. So if we zoom in and look at our graph here, 50 is increasing to 100, and then that's increasing to 200. This sounds to me like we're multiplying by 2 each time. And yeah, that is what's happening. So 50, I'll say times 2 to make that, and times 2 to make this. So my growth factor here is 2. Now let's answer questions B and C. They're asking, what is the value of y? So what's our output value when x is negative 1? So going backwards means instead of multiplying as we go forwards, it's the same as dividing as we go backwards, or you can think of it as multiplying by the reciprocal. So we're going to multiply by 1/2 instead. So the value of y when x is 1, that's going to be y equals 25 when x, I'm sorry, I misspoke, when x is negative 1. I don't think I said the negative there. So this point here would be negative 1 comma 25. And that's this one right there. Part C says, what is the value when x is negative 2? And now label this point on the graph. If we keep going with our pattern, half of 25 is going to be 12.5. So we would say y equals 12.5 when x equals negative 2. And so this one here, I would put negative 2 comma 12.5. And that's it. This assignment was only 1 page front and back. And again, I'm sorry for the copy errors if you didn't actually have number 3 included. It is still kind of important to understand how that question works. So hopefully you listened to that part of my explanation. And yeah, This was it for Unit 5, Lesson 8, the practice problems in Illustrative Math Algebra 1.